We're going to practice balancing redox reactions via the oxidation number method. Same as the rules for assigning oxidation numbers, you do not need to memorize these steps, but you do have to know how to use them. The oxidation number of monatomic ions is equal to their net charge. So silver plus is +1, and copper 2 plus has an oxidation number of +2. I'm going to keep the oxidation numbers inside circles. This helps me remember that these are not charges, but rather oxidation numbers. Copper, as an element, is going to have an oxidation number of 0. Same with silver. Now we're going to connect the relevant elements. We're going to connect silver and silver, and copper and copper. Now we also want to practice identifying those things that are oxidized and those things that are reduced. If an oxidation number becomes more positive, or if there's an increase in oxidation number, this is an oxidation. Examples would be +2 to +4. Another example would be from -3 to -1. This is becoming more positive. For a reduction, the oxidation number of an element becomes less positive. Our example, +4 to +2. Another example of becoming less positive or more negative is -1 to -3. In this reaction, silver is being reduced. It's going from a +1 oxidation number to 0. Copper is being oxidized. It's going from 0 to +2. The next step is to determine the number of electrons lost and gained. Now the rule here is that each unit change corresponds to 1 electron. Here, silver is going from +1 to 0. 1 unit change, it's being reduced. This means it is gaining 1 electron. Copper is going from 0 to +2. That's 2 units change. It's becoming more positive. It's being oxidized. It's losing 2 electrons. When we introduced redox reactions, we said they're electron transfer reactions. And what happens is, in this example, copper is giving up electrons. These electrons are being accepted by the silver ion. So the electrons lost are going to have to match the electrons gained. The way we do that is by changing the coefficients associated with each of these entities. To match the electrons lost to electrons gained, we're going to have to double the amount of silver. So now we have 2 moles of silver, each of which are changing by 1 unit. We have 2 moles of electrons being used. And coefficients associated with copper remain the same. At this point, we see our redox reaction is balanced. For any chemical equation to be balanced, there must be a balance in both charge and mass. So if we look at our equation here, we see that we have 2 silver, 1 copper, 1 copper. So we're balanced for mass. Now let's look at the charge. We have 2 silver ions that are both +1, and we have 1 copper that's neutral. It doesn't have any charge. So on the reactant side, we have a charge of +2. On the product side, we have 1 copper ion, that's a +2 charge, and we have 2 silver atoms that are neutral. They have no net charge. So we have a +2 charge on each side of the equation. Okay, so note the charge needs to match reactants and products the charge does not need to be equal to 0. It just needs to be the same in the reactants as it is in the products. All right, let's turn our attention to the next redox reaction. The first step is to determine the oxidation number. Okay, the oxidation number of zinc is going to be +2. It's a monatomic ion. The oxidation number is equal to the net charge. Chromium here is also +2. Chromium 3+ is +3, and this zinc atom is 0. So now we'll connect those things that are being oxidized and reduced. Zinc is being reduced. It's going from 2+ to 0. Chromium is being oxidized. It's going from +2 to +3. So we have a decrease in oxidation number for zinc, that's reduction, an increase in oxidation number for chromium, that's going to be oxidation. The next, we want to balance those things that are being oxidized and reduced. They're already balanced. Now we'll look at numbers of electrons. Zinc is going from +2 to 0. That's 2 electrons. We know 2 electrons are involved because the oxidation number is changing by 2 units. For chromium, the oxidation number of chromium is changing by 1 unit. That's going to involve 1 electron. The next step is to use small whole numbers to match the number of electrons lost and gained. So essentially we're looking for lowest common multiples. The easiest way to balance electrons lost and gained is to double the amount of chromium that's involved in the reaction. Therefore, we see we have 2 electrons here, and we're going to have 2 electrons involved with the zinc. Here we have a balanced redox reaction. So let's check. Balance for mass, 1 zinc, 1 zinc, 2 chromiums, 2 chromiums. So the mass is okay. Now let's look at the charge. We have 1 zinc, it's a +2 charge. We have 2 chromiums, each is +2. So we have 2 + 4, a total of +6 on the reactant side. On the product side, we have 2 chromiums, each is +3, and we have 1 zinc that doesn't have any charge, so we have a +6 on the product side. So our redox reaction is balanced for mass, it's balanced for charge. We're done.